Hello and dobre dien, buenos dias, and sabah al khair. Welcome to your preparation to Step 1 Physiology. I am Conrad Fisher and I am the Chairman of Medicine for Kaplan Medical. I have in the past been the Residency Program Director at Maimonides Medical Center, Flushing Hospital, Vice Chairman for Medicine at SUNY Downstate School of Medicine, and maybe tomorrow I'll be the pastry chef at the Plaza Hotel. But for today, here we are going to start our preparations for endocrine physiology, and we're in Section 10. Now, when you're applying for your residency, how are you seen by a program director? Well, this is how the program directors see you. Where did you go to school? What is the name of your school? What are your scores? If you're a U.S. graduate, we're going to look at your transcript. If you're an international graduate, what is your visa status? Now, everything else when you're applying gets reduced down to something you see after you're already there for the interview. For instance, you can't get your personal statement to be read before you come to interview. People don't choose who is going to come in for interview based on letters of recommendation. Now, many of you are places where you say, oh, letters get you in. But when you've got thousands of applicants in the applicant pool, no one's going to read 4,000 letters for 1,000 applicants. 1,000 applicants? Sure, because for a large pediatric family practice, internal medicine, psychiatry program, it's very easy to get 1,000 applicants. The reason that I'm saying this is because let us keep in mind, working backwards from the end, what are we doing here? Well, one, we'd like to learn some physiology and actually be able to understand the mechanisms with which underlie diseases and treatments. We'd actually be able to learn some medicine here. Number two, we're keeping in mind that this Step 1 score has enormous significance because it is the only way that people can know who you are. It's like an arranged marriage. The family meets the family. They don't know who you are. They say, what is the quality of the family? And that is why. And the family in this case is like the name of your medical school. They can't be convinced necessarily not till later on what the letters of recommendation or the research. Because the research, unless it resulted in meaningful publications, is hard to measure. So the reason why you are taking your time to be here with me, and what is that? Have you reckoned the earth much? Have you reckoned 1,000 acres much? Have you practiced so long to learn to read? Have you felt so proud to get at the meaning of books? Stop this day and night with me, and you shall possess the origin of all poems. You shall possess the origin and the good of the earth itself. So you stop this day and night with me in order to do your preparations. Why take this time and expense and extra effort beyond just looking at a Step 1 physiology book? What's the difference? What's the value? And the answer is several things. Number one, it is highly unlikely that you're going to sit there with that book for 4 and 6 and 8 hours a day by yourself uninterruptedly as you can if you know you have the time pressure of this course of videos that you're doing now. It's going to be over at a certain time. It's not going to last forever. You have time pressure. You must prepare. If you can stay at home in your house and read for 4 and 6 and 8 hours a day, uninterruptedly, on your own, without reinforcement, you probably have a psychiatric disorder. You probably need medications. So everybody needs the pressure. Even I need someone to go, Conrad, you're late. Conrad, we started an hour ago. Where are you? Even I need that. So that means you are here in order to go longer and deeper than you would on your own. Number two, there are certain textbooks, and even I, in what you may come to someday find is a massive social inappropriateness, even I, for good manners, don't want to say whose particular book, but there are a number of physiology textbooks that I have read recently, major texts, that after such a long time of knowing about physiology, I actually felt after reading them that I didn't understand anything. I actually experienced that they were so long, so complicated, so convoluted, so disjointed, that I actually think they desaturated my brain of knowledge. It's like a vacuum cleaner. It's like I took this physiology textbook and went, it actually sucked information out of my frontal lobes. The reason why it is that these physiology endeavors that we're going to do here today are so important. Number one, it's much shorter than a regular standard physiology book. Number two, it is condensed so that you're only going to learn the things that you absolutely have to know. On the other hand, when you're reading a physiology text of any kind, how would you know what the most important thing is? Well, the black and white is all the same on the page. How do you know whether it's not the point this? And that's why we're here, to be able to say, you know what? That's the super important point. That's the super important point. That's why you're here, because it will highlight it and therefore make it shorter. Instead of 1,000 words to learn, you're only going to have to learn the 75 words that are the most important. So, you're applying for residency in a year to 2 years from now. After you're finished with your Step 2 score, usually, although some people take Step 2 first. So, you're finishing your Step 1 and 2 scores, you're applying for your residency. How are you viewed by people like me who have been or are program directors? Where did you go to school? What's your visa status? What's your transcript? And what are your scores? Schools, scores, transcript. Schools, scores, visa. Everything else is afterward. Also, unlike people who take other tests where you could hide the grade, remember, failures on Step 1 cannot be hidden from the application process. Failures on Step 1 cannot be hidden because all previous attempts are there. You could hide a previous marriage much easier than you could hide your previous attempts on Step 1. You meet the new girl, you've been divorced for about 4 years, you get in love and you get engaged. You don't have to tell her you were married before if you don't want to. And there's no really good way to find out. But in Step 1, every blemish, every breakup, everything that didn't go quite so well, every set of flowers thrown in your face, every low grade gets recorded and sent in to the program directors with you. Do you know why you're taking the time to do this? Because this is a high-stakes exam. Not only does the final grade matter critically, but you can't just repeat the test like you can with taking the MCATs, where you can repeat it until you get a high grade. If you get a low grade, but you passed, you can't repeat the test. If you failed, you have to get, that goes on your transcript, and it goes out from USMLE with national reporting. So if you're not certain at the end of this process, have you done enough preparations? Then you should take more time and delay the exam. Should I delay the exam? Yes, if you're uncertain. Yes, you should. You know why? Because let's say you put off your application to residency by a year. You can have a high grade and get a great residency next year. But once you take Step 1, and if you fail or pass with a 75, that stays with you forever. So now we're going to do some of the content, Endocrine Physiology, Section 10. And the endocrinology, when you look at applied medicine for endocrinology, actual taking care of patients, diabetes, thyroid, adrenal, when you're studying now for this Step 1 part, you're going to get double value. It's like charitable contributions where you give $1 to the Metropolitan Museum of Art and Mike Bloomberg agrees to give $1 for every dollar you give. It's like double donations. Fantastic, by the way. Single largest donor to the Met, amongst other things, right? Well, for every hour you spend studying this physiology here, with just a few exceptions, every hour you spend studying physiology is like an hour studying for Step 2. Because of all the things in medicine, endocrinology as a clinical work is simply applied physiology. Point number 2. Next year, if you haven't done your Step 1, again, I know some people do Step 1, Step 2 first, but if you haven't done Step 2 yet, if you don't understand this next section we're going to do in endocrinology, and you try and learn how to manage people with hyperthyroidism and adrenal disorder and diabetes, you're not going to be able to understand anything. So the bad news is, if you don't understand it now and you decide, like, skip it, like, man, this is so difficult. I could pass without needing to learn this. I'm going to skip this. I don't like endocrine. I'm all for this. I'm going to study pathology twice. I'm going to study pharmacology 3 times. Well, you could pass like that. You could pass like that. You could say, you know what I'm going to do? You know, I'm just going to study the things I like really well and know the things I like a lot and ignore the things I don't like. Sort of like my worldview about a lot of things, you know what I mean? Okay? So, but the thing is, you could do that. But your goal is different than just passing. Your goal is to get really high grades. Now, these tapes that we're doing here, these video projections and the live classes, long ago ceased to be, let's just pass. Please, please, 1 inch, please, let me just, no, it's not like that. We're here to get 250s and 260s. We're not here to just pass, okay? We're not here to pass. We're here to kick ass. Now, that means that the physiology you're doing now is the same as what you'll need for step 2. So an hour studying this is like 50 minutes towards studying step 2. You can pass without needing to know much of this. You can just continue to pay attention to the thyroid and diabetes you always knew and ignore the rest. But you cannot excel without it because endocrine is the single largest section in the whole part of the course. Oh. Now, the first thing in endocrine physiology is to simply understand the mechanisms to which hormones work at the individual cell. Now, it is not enough to say the hormone attaches to the receptor and, things work, man. Oh, yeah, the hormone touches to the receptor bone and the receptor bone touches to the action bone. No, it doesn't work like that. It's extremely important that you be able to distinguish the difference in the mechanism of action between steroid-type hormones and peptide-type hormones. Now, first of all, I'm going to say it, and then we're going to look at the picture, okay? What this slide is about is understanding that steroid hormones are slow. I'm going to say it fast first. Ready? Steroid hormones are slow. They have long half-lives. They're protein-bound. They need time to reach their action. They need time to result in the production of a protein later on. So steroid hormones are slow with long half-lives that need time to result in an action. Now, peptide hormones are fast with short half-lives. They're not protein-bound. They have their effect instantly, and then they're gone. They're not protein-bound, so they go by the kidney and they get urinated off. That's the fundamental difference between these two things. Steroid slow, peptide pops. Steroids are slow and a peptide pop. Steroid protein-bound and a peptide is a water-soluble. Steroid doesn't get urinated off. Peptide does because it's not onto albumin or a carrier protein. That's the big thing here, okay? You see, the difference between steroid hormones and peptide hormones is like the difference at lunchtime. Do you go and make bread and make a sandwich and bake the bread and do the cooking? Or do you go downstairs to the store and get a sandwich that's ready made and unwrap it? Peptide hormones is ready made. You just unwrap it, activate it, you're on. Steroid hormones are slow. It's like going downstairs, buying the food, cooking the food, preparing the food. Much slower, but still effective. Let's look at this slide. Now, steroid hormones. Now, I know here it says steroid and thyroid hormones, and steroid hormones and thyroid hormones work as a steroid hormone. Now, steroid hormones, do you use cholesterol? No, I don't use cholesterol. Oh, come on now, you must be using cholesterol in your cells. Oh, no, I'm not using cholesterol. Well, maybe you're using something like cholesterol. Maybe a steroid. Oh, it's kind of like this. Hey, do you have a chancre? No, I don't have a chancre. Maybe you got something that's like a chancre. Maybe you've got a chancroid. Do you have erysipelas? Do you have pemphigus? No, I don't have pemphigus. Maybe it's got something that's like pemphigus. Pemphigoid. Carcinoid. Hey, are you a man? No, I'm a machine made in the image of a man. Android. So when you see the word steroid, the very word steroid means similar to, derived from, similar to cholesterol. So when you see this word steroid, it means like cholesterol. Like cholesterol. Okay. So first, the name of the hormone actually helps us. Remember, aldosterone, steroid. Testosterone, steroid. Progesterone, steroid. Estrogen, close enough, babe. The only one that doesn't have the name that helps you, thyroxine and 1,25-dihydroxycholecalciferol, because they're not derived from a steroid nucleus, but they function as a steroid hormone. Here, let's look at this diagram. The steroid hormone, you notice that there's no effect here on the surface. There's no cell surface receptor. It goes through into the nucleus. So the effect, the target of the steroid hormone is that it goes into the nucleus. It is not at the cell surface. It goes into the nucleus. Now that needs time to make the messenger RNA. That needs time for the messenger RNA. What is the message? The message is, hey, Mustafa, make a protein. That's what it's like. Hey, Bob, make a protein. What's the message? Make the protein. Now, peptide hormones are not like that. The protein's ready made. When I say peptide hormone is like going to the store and getting a sandwich. It's already made. Unwrap it. Neat. This is the fundamental biggest difference. Steroid hormones, you're making a protein new. Peptide hormones, you are activating a hormone, a protein that's already made. This is the biggest fundamental difference, and you must know it. Now, the steroid hormone, because it's slow, there's a long half-life, protein bound. Now, that is in general the case, except the one exception. What's the only one that's not protein bound? DHEA, adrenal androgen. DHEA, dehydroepiandrosterone, is water soluble because it's sulfated, just like me. The big ass here on my chest. Do you see? Sulfated. Sulfated. It's sulfated, so it's water soluble. DHEA is the only exception. All steroid hormones are on protein carriers except DHEA, which is sulfated. And that has to do with stuff that we'll do later at the end of the endocrine section. It has to do with how it is that when you're pregnant, that the mommy can use the baby's adrenal glands to augment her own estrogen supply. Now, peptide hormones, over here. Peptide hormones, the peptide hormones have a cell surface receptor. Now, this thing about the cell surface receptor, remember, a cell surface receptor and the G protein, even though they look the same, the receptor and the G protein are not precisely the same. Ready? The membrane receptor, the G protein, does the peptide hormone attach to the G protein or does it attach to the receptor? It attaches to the receptor. The peptide hormone attaches to the receptor. The receptor activates the G protein. The G protein causes the effect inside the cell. And again, once more with feeling, yeah, the peptide hormone attaches to the receptor bone, and the receptor bone attaches to the G protein bone. So, the peptide hormone attaches to a receptor. That's where it touches. And then the G protein sends the second messenger. When you want to turn the lights on and you touch the switch on the wall, you're not touching the electrical wires inside the wall. You're touching a receptor. You're touching a wall plate. Underneath it in the wall, there is another mechanism that actually sends the electrical signal out to the lights. And that's very similar in the cell. In the cell, you attach to the receptor. The receptor sends the message through to the G protein. The G protein sends the signal through to activate the peptides. When I touch the light switch on the wall, I'm not touching the electrical wires. I'm touching a receptor which activates the box inside, which sends the electrical second messenger to the ceiling lights. So second messengers, there are various forms of second messengers depending on the hormone. Now, Cyclic AMP activates things fast. Some things will calcify. Some things will calcify. IP3, that's inositol triphosphate. IP3, that's inositol triphosphate. That's because some things have a fast activation by phosphorylating them. Bang! Phosphorylating. Woof! Like Harry Potter. It's like the magic rod. That's what I think these G protein. G protein is like the wand for the wizards. You know what I mean? Okay. The receptor is the hand. The G protein is the wand, and it sends out poof, cyclic AMP, poof, phosphorylate, poof, calcify. DAG, man. What is that? DAG. DAG. Okay. Now DAG, diacylglycerol. Diacylglycerol is just another second messenger. Diacylglycerol. These second messengers phosphorylate protein that's already there. So you see when it says the protein there? That protein is already made. It's already made. And that's the fundamental big difference between steroid hormones and peptide hormones. Peptide hormones have proteins that are already made and you're just activating them. And that's the difference. That's the difference. So let's go on to our next slide. Now, fundamentally, this looks at our class of hormones, what we just said here. And we see here on the left-hand side, we said our steroid hormones. Steroid hormones, we said they're lipid-soluble. Lipid-soluble means that they are protein-bound. They're all protein-bound with the exception of DHEA, adrenal androgens. So they're all protein-bound with the exception of DHEA, adrenal androgens. Because they're protein-bound, they have a long half-life or a short half-life? Long half-life. Protein-bound means a long half-life. Protein-bound means a long half-life. Next thing is, you have to have the effect, there is no surface, it's inside the cell, and it is new proteins. So there we go, steroid hormones, lipid-soluble, inside the cell, new proteins. Exceptions for not lipid-soluble is DHEA. The other thing is, steroid hormones and all hormones, a fundamental characteristic of all hormones is they're made in a pulsatile nature. They're made in a pulsatile nature. That is the fundamental characteristic of all hormones, man. They're made in a pulsatile nature. That's the nature of the beast of our endocrine system. The fundamental nature of the endocrine system is impulsivity. Except thyroid. Thyroid is the only one that's made constant. Thyroid is released all the time. Thyroid is constant because we don't want our metabolic activities to have different biological temperatures and speeds. Thyroid is constant. Thyroid is constant because when you get up in the morning, you don't want to have a body temperature of 78 degrees and in the afternoon have a temperature of 107. Biological processes cannot work at a 20-point temperature spread. Biological processes has to have constancy. That's why thyroid hormone is constant. Constant for the thyroid hormone. Not until the sun excludes you do I exclude you. Not until the waters refuse to glisten for you and the leaves refuse to rustle for you shall my words refuse to glisten and rustle for you. Constancy, constancy. So this constancy here is a feature of only thyroid hormone. Everything else, pulsatile. Now, water-soluble hormones are always on the outer surface. Water-soluble hormones always have a second messenger, of which cyclic AMP is just one. Now, insulin doesn't use cyclic AMP. Insulin has its own mechanism. Insulin has a mechanism of a receptor called the tyrosine kinase. Insulin has a mechanism of a tyrosine kinase. So insulin has its own mechanism of a tyrosine kinase. Next slide. Now, lipid-soluble hormones, let's be clear about this, they're all pulsatile in their activity. They're all pulsatile in their activity, except lipid-soluble hormones are actually synthesized. Lipid-soluble hormones are actually synthesized as needed, but even though the peptide hormones are stored, they're not released constantly. So they may be stored. So you might say, hey, fishy, fishy, fishy. I thought you just said that it's all pulsatile. Here it's stored. That's true, but they're not in action. The fundamental characteristic about the endocrine system is that you're only in action in a pulsatile nature. Unlike the hormone system. Pulsatile. Up, down, everywhere. I'm both stored and I create new synthesis. So, peptide hormones, steroid hormones, their action is pulsatile and impulsive. Although one may be stored and the other is not. Now the reason why also that the water-soluble hormones can be stored, you see this word stored in vesicles? What are the vesicles made of, huh? Well, the vesicles are made of lipids. You can't have a hormone made that is lipid soluble stored in a vesicle made of lipids. You can't have a hormone that is lipid soluble stored in a vesicle made of lipids. That would be like trying to store me in a cage made of butter. You know, you can't, or bread. You can't have me stored in, that's why we don't make prisons out of bread and butter. You know, you can't store somebody when they're made of the same stuff, man. So that's why it is that lipid-soluble hormones can't be stored in vesicles, because they're lipid-soluble and the vesicle has lipids. Now, I have some good news and some bad news about that. Since they're not stored, they're dissolved in plasma. So if they're not stored, after they're stored, then they get dissolved. Then they get dissolved into the plasma. Now, because they're not protein bound, that's why it says short half-life. The more the protein binding, the longer the half-life. So, peptide hormones are free, not bound. That's the same thing as saying short half-life. Now, all peptide hormones are dissolved free without protein carriers, except IGF, insulin-like growth factor. Except IGF, insulin-like growth factor, is a peptide hormone that is a protein carrier. Very important, because it's part of the reason that you can measure for acromegaly and giantism and other forms of overproduction. You measured the IGF, insulin-like growth factor level. IGF level is a peptide hormone, but it's protein bound. Peptide hormone, but it's protein bound. All hormones are secreted in pulsatile nature, except thyroxine, constant. All peptide hormones are free, no protein carrier, except IGF, insulin-like growth factor. Steroid hormones are all protein bound, protein carrier, long half-life, except DHEA, adrenal androgens, sulfated. Next slide. Now, the carrier proteins. This slide brings up the subject of the carrier proteins. Now you'll notice where it says cortisol binding, thyroid binding, estrogen binding. What this means is that steroid hormones, because they're lipid soluble, they can't float around free in the plasma. Hey, in your interior world, inside of you, do you live in a watery world or do you live in a fatty world? Living in a world inside. Your world inside, in the plasma, is mostly a watery world. That's why we don't have olive oil for blood. We have blood that's mostly liquid, not olive oil. I don't have olive oil for blood, and I don't poop hummus. I have watery blood, and that's why it is that in the watery world inside of me, the steroid hormones, which are lipid soluble, are not going to do well in that watery world. Onto the albumin. Now, all of them have to have a protein binder that's specific. Cortisol binding globulin, thyroxine binding globulin, sex hormone binding globulin. Hey, I don't want my highly valuable, hard to make cortisol, which I struggled to make. I've been working in the adrenal all day long in this pathway. Yeah, Yeah, my fasciculata, yeah, here I am cooking and cooking and cooking to make cortisol, and all you do is go over to the kidney and piss me off. No, we can't have that. We can't have that estrogen, which you have been so lovingly making all day long, making your ovaries clicking away from me, having an energy investment. Cholesterol is energy, right? It takes time and steps. We can't just have you going over to your adrenal, take everything out of the adrenals, the ovaries, and the testicles, and just urinate it off in 2 seconds. We want it to stay constant, and we want it to stay in the gonad. So we have a binding globulin. Why is it that the saturation of my testosterone is greater in your favorite Greek philosopher? You've heard of Sophocles. You've heard of Socrates. You've heard of Aristophanes. Now your favorite Greek philosopher? Testicles. How is it that we keep our sex hormones where they belong, down there in the testicles? Because the sex hormone binding globulin, that's what prevents it from circulating off to my ears or my elbow. I don't want that testosterone over here in my elbow. I want it to keep saturated down there in the seminiferous tubules where it belongs. And also, these are energy-dependent steps. We don't want them urinated off. We want them around constant for a long time. Now, that also means that if you have liver disease, you're not going to make those binding globulins. That's the other thing here. What automatically lowers the binding globulins? Liver disease. What automatically lowers the binding globulins? Liver disease. Because they're made in the liver. Next, what automatically lowers the binding globulins? What other organ disease? You ready? Disease of which of the following organs would be associated with a low total steroid hormone level? We already said liver disease. Disease of which of the following organs would be associated with a low total steroid hormone level? And the answer is, would it be disease of the stomach, duodenum, colon, kidney, lung? And the answer is kidney. Why? We have cortisol binding globulin, thyroxine binding globulin, sex hormone binding globulin to keep that stuff inside the body because it takes energy to make it. We don't want to piss it off. It's like building a new car and then driving it off a cliff. But why is it that kidney disease will result in a low total level? Nephrotic syndrome. When you have nephrotic syndrome, you have now a hole. It gets pissed off. Nephrotic syndrome results in all the steroid hormones in my toilet because now I got a hole in my kidney big enough to lose those hormones. Oh, disease of which of the following organs will result? The other way to invert the question like this for step 1 is it says like this. Here's a person who's got long-standing diabetes and hypertension, most common reason for nephrotic syndrome, by the way, diabetes, hypertension. You have a disease of any kind, you don't know what to say, and it says cause, say diabetes and hypertension. And you have a person with long-standing diabetes and hypertension. Which of the following blood levels do you expect to be down because of it? A, growth hormone, peptide hormone. B, LH, peptide hormone. C, FSH, peptide hormone. D, any other peptide hormone? The answer will be a steroid hormone. The answer is, what does the nephrotic syndrome, what do you expect to be down? Is you'll expect it to be down with the steroid hormone because the peptide hormones get urinated out anyway. Now, peptide hormones don't travel bound. So since they're not bound, with the exception of IGF, they're all free all the time. All free all the time. All free all the time. It's like, okay, okay. Like a woman who refuses to ever ultimately get engaged and married. Been engaged, yeah? Okay? So the thing is, all free all the time. Free all the time means no protein carry. It has an action. Now, if we look at this slide here, very important concept is called that only free hormone has a target organ effect. Only free hormone has a target organ effect. Only the free hormone is having feedback inhibition. Only the free hormone has a target organ effect, has feedback inhibition, and is regulated. Only the free. The same way, you drove to work, you drove to school this morning. 50 people drove to work this morning. 49 of them stayed in their car and only one came out and into the building. Who's going to have the effect? Who's going to be regulated? Who's going to get the feedback inhibition? If you have 50 people driving to work today and 49 of them stay in the car or 49 of them stayed in the subway and only one come out, it's very similar. You see, city buses and protein carriers are very similar. It may transport it around, provide some protection, but there's no action, man. No action. Only the free is regulated. Only the free has feedback inhibition. Ding, 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 ding. The woman becomes a pregnancy. Ding, 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 ding. And which of the following will go up? Ding, 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 ding. Free T4, total T4. Which of them goes up? Free T4, total T4. Thyroxine. Ding, ding, ding. In pregnancy, which one goes up? And the answer is the total goes up. Why? Testosterone and androgens decrease binding globulins, whereas sex hormones, female sex hormones, increase binding globulins. Liver disease, decrease binding globulins. Nephrotic syndrome, you lose those binding globulins. Androgens decrease binding globulins. But female sex hormone makes the binding globulins. Androgens decrease, estrogens increase. That's why all pregnant women have an increased total thyroxine, total T4, excuse me. They have an increased total thyroxine or T4 because the binding globulin goes up. So the total goes up, but the free remains constant.